Hello friends, so welcome to the second lecture of Harmonic Oscillator, and this is lecture number 21 overall. So we will continue what we have been discussing in the last lecture that we left at here. So we framed the Schrodinger equation for the quantum mechanical harmonic oscillator, all right? And it's needless to say that the value of x, the limits are minus infinity to plus infinity. Okay, so the question is how to solve it and what are the solutions. Okay, to answer this thing simply, that there is no easy general method to find a solution of this Schrodinger equation. Okay, this differential equation. Yes, you may try. So it requires a considerable knowledge on mathematics, and in fact this solution can exactly be solved by a power series method, which is quite mathematically demanding. So in this context we are not going to discuss the way of solution of this equation. Rather we will directly focus on the outcomes, that means the solutions. So if we at all solve this equation, we will get well-behaved finite functions or wave functions as a solution of this Schrodinger equation, and that would give us that the energy of the harmonic oscillator of course depends on n, and it is given as En is equal to h cross root over of k by m n plus half, where n is equal to 0, 1, 2, 3, etc. and n can go up to infinity. All right, so just a moment, my mouse fell off. Okay, all right, so now we are ready to go. So probably you have noticed one mistake over here, since we were using the vibration of a diatomic molecule as a model of quantum mechanical harmonic oscillator. So instead of m, we must use the reduced mass mu. Okay, so now this is all right, and so what we can write also, that this is h cross omega n plus half. All right, and we can further write it is h by 2 pi omega n plus half, and since omega by 2 pi or omega is equal to 2 pi mu, also we can write it like this: h multiplied by omega by 2 pi, that is nu, frequency in hertz, this. Okay, so overall this is a pretty famous equation in terms of vibrational spectroscopy or IR spectroscopy. So now let's look at the situation here. So n can be 0, so n is equal to 0 won't give you a trivial solution here, that is number one. And then of course what happens when n is equal to 0, so we call it E0 is equal to, n is equal to 0 means this is h nu divided by 2 or half h nu. So this n is equal to 0 corresponds to a term, it's called the 0 point energy. Okay, so basically the 0 point energy is the ground state energy. So we can draw once again the energy levels. So suppose if I can plot x in this axis and potential energy u in this axis, so definitely we can draw a perfect parabola like this. All right, and then since energies are quantized, we can draw this level like this, okay, where Here n is equal to 0, 1, 2, 3, 4, etc. So n is equal to 0 means this level. All right. So this level is my ground level, and it is known as the 0-point energy. So now the question is, what is the significance of having a non-zero value of the 0-point energy? See here, h is a non-zero value, nu frequency is a non-zero value. So at the ground level, the energy of the quantum mechanical oscillator is non-zero. Okay, so what's the meaning, significance of it? So significance of it is simply that this is the value E. Okay, means the total energy E. So we know E is equal to U plus T, potential energy and kinetic energy. So potential energy can be given as half kx square, and plus kinetic energy is p square by 2m. So now you see that this is equal to 0 means this is a square value positive, and this is also a square value positive. So the summation of two positive value is equal to 0 means that both, okay, that both x square should be equal to p square and should be equal to 0. Now if individually x square and p square is equal to 0 means we can say that as if the x is equal to p is equal to 0. So the moment if you write like this, so that means you can precisely tell the position is 0 and the momentum is 0, and the moment you write this, that means you are violating Heisenberg's uncertainty principle. Okay, so therefore quantum mechanically 0-point energy can never be 0. It should be always half h nu. All right, good. So now we will erase the board and we'll talk about the nature of the solution. So look at here, we have only talked about the energy, because if we solve this we'll get E psi is equal to H psi. Provided we know psi, we know E. But what about psi or psi n? So for this, let's continue our discussion. Okay. All right. So here, look what I have written on the board. We have some pretty lengthy expressions. Okay. In fact, as I told you that it requires a power series method to solve such kind of differential equation, and the solution that we get, these are not a very simple functions that you have already seen. So the solutions, that means the wave functions, they involve a kind of polynomial called Hermite polynomial. Watch out, so there are many H related terms, right? Hamiltonian operator, Hermitian operator, and again we have Hermite polynomials. So these are different. Now for every value of n, we get a non-degenerate wave function psi n. Okay, so we don't get a situation for degeneracy here in quantum mechanical harmonic oscillator. So this is the general form of psi nx. So psi n as a function of x, it is expressed as nn, which is the normalization constant. So this is how the normalization constant works. 1 over 2 to the power n factorial n whole to the power half, means root over, multiplied by alpha divided by pi whole to the power 1 by 4. So this is already a complex expression. And then the Hamiltonian, these Hermite polynomials. So Hn stands for, or Hn alpha to the power half x. Okay, so this itself stands for the Hermite polynomial. So this can be represented as Hn zeta, where the n stands for the nth degree polynomials of zeta. Okay, so you see here Hn, and within bracket whatever these terms, depending on the value of n, we have an expression for Hn alpha to the power half x. So we simplify it in terms of zeta here. So then when n is equal to 0, we can easily find out from here. Okay, so when n is equal to 0, no, sorry, not from here, this is the normalization constant. Anyway, this Hermite polynomial, for n is equal to 0 stands 1, and for n is equal to 1 it stands as 2 zeta, and for 2 4 zeta square, and so on. Here is a cubic function, here is a quadratic function, etc. All right. So from this, definitely we can try to find out what should be the value of psi 0x. Okay, so that we can try to find out. So for n is equal to 0, we have this value. So 1 over 2 to the power 0 means 1, factorial 0 means 1, root over of 1 means 1. So this value is 1, and we have only alpha by pi to the power of 1 by 4. And then for n is equal to 0, here we have this Hermite polynomial a0 zeta is equal to 1. So basically this entire part, this part becomes 1. So we have this unity multiplied by e to the power minus alpha x squared divided by 2. So that is your h0x. Similarly, you can calculate h1x, h2x, etc. All right. So now I am giving you some homework. That is, you need to do the following stuff. The first, to find out what is the value of psi 1x and what is the value of psi 2x. All right. And then you find out that in fact psi 0x is a solution. That means you take this value of psi 0x and put in this equation and try to validate that the right hand side is 0. That is number 1. And then number 2, that you prove that both, okay, psi 0x and psi 1x are normalized. Okay, so these are cross verification. I know this is already normalized because we have taken this normalization constant this manner, but it's your job to find out that using the correct normalization expression that value equals to 1. That is the one thing. All right, and after that we will try to prove that orthonormality condition, that psi 0 and psi 1 are orthogonal, or psi 1 and psi 2 are orthogonal, or psi 0 and psi 2 are orthogonal. So that means for any two value of n, n1 and n2, we have to prove that these solutions, okay, are orthogonal. All right. So we will do that in the next proceeding sections. But now it is the time to quickly try to draw the graph plot of psi and x versus x. All right. So we will plot psi x versus x and psi x squared versus x, means the amplitude function and the probability density function, and that is a common practice, and we already have done it for free particle in a one-dimensional box. We will just extend the same thing over here. Okay, so let's quickly draw it out and clear our understanding. Okay, so let's do it. Okay, so this, in the left hand side I have drawn the amplitude function versus x, and here the probability density versus x. So these are the energy levels corresponding to n is equal to 0, 1, 2, 3, and corresponding to that we have only energy levels, okay, according to that quantum number h nu by 2, 3h nu by 2, and so on. So we definitely see in harmonic oscillator the energy levels are discrete in quantum mechanical domain. So as you see, I have also drawn a parabola in both sides. Okay, so these two parabolas has no significance in quantum mechanics, but I have drawn it to show you that what happens when the same system is compared with the classical analog, or with the classical picture. Okay, so classically the harmonic oscillator should have the potential energy from here to there. Okay, so it would vary like this. Okay, so we'll come to that later. But in quantum mechanics, when n is equal to 0, the amplitude function would behave like this. Okay, you see everything is, all phase is positive. Okay, So, and correspondingly the chi-square goes like this. So it's kind of a Gaussian distribution function, and this chi-square is the same thing. And then we have the phase changes over here when the displacement goes to either negative side or positive side. But we have double lobes because probability is always positive. And symmetrically we have situation for n is equal to 2 and n is equal to 3 and so on. But you should mind two things, that you see here the amplitude function, it expands beyond these two limits of internuclear distance, means the relative distance between the two nuclei. Okay. And also to some extent the probability also spills out of these 2 points, and this is not done by a mistake. So there was a definite significance why we have drawn the diagrams like this. So sometime later I will try to discuss that why there is a difference, that why exactly we did not draw something like this. Okay, so there is a difference between the two, why this and versus this. So that means there is some difference between the classical picture and the quantum mechanical situation, exactly in terms of the internuclear relative distance. So we will talk about that later. But anyway, this helps us the understanding of the graphical picture. But your job is to take any value of say chi 0 or chi 1 and chi 2, you find it out, and then you verify that this graphical picture follows exactly the equation side by side. All right, so good. So now let's move on to the next section, that we have to understand the nature of the amplitude functions a little bit more detail. Okay, so let's do that. Okay, so in this part we will try to learn about odd functions and even functions. So the Hermite polynomials that we encounter here in this chapter can be classified as either even or odd functions. Now what are even and odd functions? That probably you have already familiar about it. So I am just refreshing your memory that if a function looks symmetric over minus infinity to 0 versus 0 to plus infinity, means both in the negative and positive side, then these are called even function, and we define it as something like this. So even function means that f of minus x should be is equal to f of x. Okay, and so that's even. And in odd, the function would behave asymmetrically with respect to the positive and negative sides of x. So here the curve looks like almost the reverse of the mirror image. So here the two sides are mirror image to each other, and here this curve is a reverse of its mirror image. So basically this is asymmetric. And the definition of odd function, we can write that f of minus x should be equal to minus of f x. Okay, so f of minus x, or sorry, yeah, so that is the odd function. All right, so now let's take some examples to see whether these are even functions or odd functions. So the examples of some even functions are x square, e to the power minus x square, cosine x, etc. And examples of some odd functions are x cube, the sine x, and x e to the power minus x square, etc. And not necessary that all the functions can be classified as even or odd. So there are functions that cannot be even, cannot be odd. So the functions that we are unable to classify as either even or odd, we can definitely tell that this is neither even or nor odd. So these are e to the power x, x plus x square, and then natural log of x, or say sine x plus cos x. Okay, so you can see that the majority of the functions probably is neither odd nor even, but some of them can be classified as the even function or the odd function. So you can try, so test whether the following functions that I'm giving you, x multiplied by sine x, e to the power minus x square cos x, okay, and then x square sine x, and then finally e to the power ix. So whether these functions are odd or even, or neither odd nor even, that you have to find it out. Okay, so now remember one more thing, that the product of two odd functions, okay, gives you even functions, and the product of any odd or an even in either order gives you odd function. Okay, and definitely the product of even and even function gives you even functions. Okay, so here for example you have even function x square and e to the power minus x square. So x square times e to the power minus x square would give you an even function. All right, and here you see e to the power minus x square is even function, and x probably is an odd function. So odd multiplied by even would give you an odd function. All right. So now let's come back to our original point of discussion, that Hermite polynomials are either even or odd. So can we just quickly classify the first few Hermite polynomials, whether these are odd or even? So let's quickly erase this board and let's try it out. Okay, so let's quickly find out that h0 zeta is equal to 1, and so definitely it's an even function. And then h1 is equal to even, because see, there is no way to put the value of x, so this is always positive, so that means we can consider it as even. And then h1 zeta is equal to 2 zeta, so definitely it's odd, because depending on zeta is equal to positive, it is positive, negative, it is negative. Okay, and h2 zeta, h3 zeta you have to find out. But what's your expectation? Of course, so you expect that these to be even and these to be odd. Okay, but you please find out from the expression that I have already given whether h2 zeta and h3 zeta conforms to the even and odd functions respectively. All right, so now why we are doing this? Because if you look at this integral, okay, fx dx from minus a to plus a, so it could be either minus infinity to plus infinity, doesn't matter. Okay, means over a complete cycle, means over a limit which goes from like the same value of minus limit to plus limit. It is not like 0 to a or 0 to infinity. Okay, this is always 0 if fx is odd. All right, and you can easily verify. Anyway, so this has some definite significance in context of our harmonic oscillator. So what is the context? So now look at this here, that we have this thing psi nx. Okay, so this is one of the solutions of harmonic oscillator. So now we can see that depending on n, okay, so here this is the value. Okay, so depending on n, it could be even or it could be odd, of course. All right, by looking at the nature of these polynomials or the entire solution, you can tell. So then what should be the expectation value of the displacement, average displacement? You can recall, then it gives you, according to our context, minus infinity to plus infinity, whatever you take, psi nx star, okay, and then x cap means x here, psi nx dx. All right, so what should be the value? Now n can be even or odd. So if n is even, so these two product will give you even, x is odd, so the total is the odd function. And both n are odd, okay, or both n are even, the product is even multiplied by odd is odd function. All right, now what if one is even and another is odd? Okay, of course, so that won't be happening because we are taking this same psi n. Okay, so I mean n here, it could be either even or odd, so they can be different because it's the same function and we just take the complex conjugate. Okay, so depending on whether n means irrespective of n is either odd or even, this entire function fx becomes odd, and definitely this integral gives the value of 0. Okay, so you see immediately we can tell that the average position in a quantum mechanical harmonic oscillator, or the average displacement, is 0, or expectation value of the displacement is 0. All right, so that is not surprising because we have assumed that it vibrates symmetrically with respect to the mean position, so the average displacement is always 0. All right, but there is another thing, that is the Kronecker delta. All right, so what should be the value of the Kronecker delta? Because for Kronecker delta, we take any two things. So then that, in that case, so we can express it like this. All right, dx. So here we are facing a situation for odd and even. Okay, so m could be even, n could be odd, n could be odd, or m could be even, something like that. But easily we can tell that okay, so definitely this is from minus infinity to plus infinity, that if either of them is odd and other is the even, so definitely we can prove that this value is 0, so that means these are orthogonal. Okay, but what happens that if m and n, these are not either even or nor odd, so it could be both even or it could be both odd, and then definitely we have to calculate the integral. We cannot predict the orthogonality value to be 0 by this method. Okay, so I hope you understood. So now we are in a position to handle such kind of integrals in order to find out many things. That means the average position, average momentum, and then Heisenberg's uncertainty principle and its verification in harmonic oscillator problem, and also the cases of Kronecker delta. All right, so this knowledge of odd even function and these integrals would help us a lot. Okay, so I hope you understood whatever I tried to explain in today's lecture. So please follow the video lectures, and we will see you in the next video lecture session, and we hope to wrap these chapters pretty soon. Okay, so till then, goodbye.